Our first speaker is Alexis Arnaudon from the Imperial Martin Healthcare Center. And Alexis will speak about inferring uncertainties in computational analysis.
Okay, thank you for inviting me to this nice workshop. So yeah, I'm part of this one of the fifth center, and then what we do is actually just for a bit of advertisement. We do more networks, graph theory-based approach to healthcare, precision healthcare. So between imaging and machine learning, you can do a lot of things with graphs. So we are trying to play with this. But today I'm going to talk about previous work that I did during my PhD with Alexis at Imperial College, and a collaborator from the University of Copenhagen in the computing department about more imaging and computational anatomy ideas. So I was working with Alexis, so maybe you know the name. He have developed this LDDMM framework we've heard about before. So for us, the religion is LDMM, so we shouldn't do anything else than LDMM somehow. So I want to show you how to try to perturb LDMM a bit, and by inserting noise and try to model this, to say this is a model of uncertainties or variabilities of images we can observe in data and so on. So, but by being in this region of LDMM, so that's my aim. Okay. So the way I want to explain LDMM is by analogy with fluid mechanics. So the first image is from Google somewhere in the internet. You see it's a video. We have two vortices, some colliding, and so this one is like rotating clockwise and counterclockwise, and then they move, interact, and then all these nice, interesting patterns between them. So you can see in this image you have like two scales. You have like big blobs that move and interact, and you have this fine, noisy kind of pattern between them, right? So then I'm telling you the equation of motion for the fluid is just this Euler equation. So if you know it, it's fine. If you don't know, it's okay. It's a nonlinear equation, right? V is the velocity field, so it's little arrows at each point telling you in which direction the fluid is moving. And then you just need to solve this, put in the computer, and you get these videos, right? So the way I do image matching is really taking two snapshots of the simulation of this and trying to make sure that the first one and the last one corresponds to your input image and final image, and trying to find what is V of t that matches the first image to the last image, right? So that's just giving a kick to this picture and then trying to move this blob to there such that it corresponds to, for example, the last image you want to have. So in terms of mathematics, we want to describe it in a general way, so we can actually understand what the mathematics are behind this equation, right? So I don't have time to do this, so don't look at the equations, just listen to me. So what we do is look at the fluid as being little parcels of fluids, like this little box, which are here, and then we just look at how they move in space. So we just have this R, which I call here phi, which just moves this little box in the reference frame to the actual position that depends on time. So it's really this phi here. Then we look at the velocity of the parcels, which are just time derivative of this guy, right? But then I want to look them as if I'm here and the fluid it passed through me. So I need to do this little composition here from the speed phi dot of the parcels and taking it back at the position where the fixed position in space, so I can really see the fluid passing through me. So this is called Eulerian variables. And then if you do this trick, instead of having Euler-Lagrange equations for phi, you have this kind of weird equation which is called Euler-Poincare equations for V. And this is just saying we have a diffeomorphism underlying the structure. So we have these inversible maps which are phi, so we can write the inverse, and by imposing this we get the equation of motion which are the Euler equations for fluid dynamics. Right? So then we have this abstract notations here, just this guy is just V dot grad V, roughly. So if L Lagrangian is just kinetic energy, V squared, you get this is V dot plus this term which looks like this, right? Fine. So then you say, okay, then we actually want to get rid of the little noisy things between the vortices and just track the vortices. So what we do is we say let's convolve a certain M to get the V, and this M is actually just a bunch of delta functions centered at the vortices. So I want to track the vortices with position Qi t of t and momentum Pi. So if I'll just say get those bunch of n particles, and I convolve this with some kernel, which is here the peak kernel. You can choose a Gaussian kernel. Then you have like blobs moving and interacting, And then the equation of motion, then it becomes a bit more complicated because you have m and b's. You have to make sure which one is correct, and this actually comes from this term here. And then you can say, if you assume this form of the momentum, then you can actually reduce the full PDE in terms of just a bunch of points parameterized by p and q's. So if you have n particles, you have four n variables, x and y. And this turns out to be a Hamiltonian system. So you have Hamiltonian here, which is just kinetic energy with nonlinear interaction terms. So particles, when they get close to each other, they don't want to be close to each other, so they repel themselves, so they just bounce and those kind of things. And the interesting part is by having this geometrical description of the system, we know that if we solve this system as an ODE system, which is very low dimensional, then we can actually convolve it back, and then it's a solution of this one, which is a solution of this for those 2 point vortices, given some alpha parameter, which is how much we actually remove all those fine scales tolerance flows. So this is the way I try to explain the LDDML approach with landmark dynamics. So this is just landmark dynamics. So you put those points into the image, and then you're trying to match points to points. Then you can interpolate between the points to get the full deformation of the image, right? Okay, so then, so this LDMM, and like this picture is like this big brain damage, large deformation, right? And this is actually, we saw this from previous talks, so it's just putting some bunch of points here and trying to deform those points to get to this one, for example, which is a sign here, but anyway. And then you can actually interpolate with kernels around it to deform the image nearby, right? So what we want to do is just, given initial positions of the landmarks and final positions, we just want to optimize kinetic energy, so get geodesic trajectories. So from H to D, it's just finding the initial kick. You put initial kick for each position on the D to get after a time, certain time 1, to get to H. So it's how to move the fluid, give a kick in the fluid such that it turns and then matches the final one. Now the question with uncertainty is you have many images like this, and then you say there's no true one, there's no best final one. You want to try to predict how many variabilities. You see they're all different, but they should be all the same somehow. So we want to have one mean best trajectory and then variability around it. So we want to characterize how much of this variability we have. But we want to preserve the diffeomorphism. So we want to be always invertible, and we want to preserve the structure of having the full PDE with noise, then reduces to a set of ODEs. So we can solve it quite efficiently. So the way we do it, we just, so I skipped many slides here, but at the end of the day, what we get is just the same ODE for P's and Q's, plus some noise term here, which are quite different from the usual stochastic forcing, where you say each particle has some randomness on it, and then they just oscillate, they just randomly move, which would be just additive noise in the momentum. So you just have like random kicks on each particle. Here, what we do is we say we have this sigma of Q, which are also any function of the space, but we take them as quotient kernels. So if a particle moves on this phi of Q, then it feels the noise. If it's far away from the center of this blob, then it doesn't feel the noise. So the noise is attached to the image, if you want. So it's more like an Eulerian noise, whereas this is just a noise attached to the particle itself, describing the image. And so if you have this clever kind of terms, you can actually show that this is a reduction of the stochastic PDE that describes some kind of stochastic motion of the fluid. So if two particles are next to each other, they will feel the same noise. If they are far away, they will feel different noise. In this case, if they are close to each other, they will feel different noise anyway. Anyway, I mean, doesn't matter the distance between them. So it gives a very different type of model for the uncertainty of your matching. So the easiest example just to illustrate it is just to have I think 100 landmarks on this black curve. So we don't see the landmark, but you have a bunch of points. So deterministic would just be translations to this dash curve. Now if I add the standard noise, so we just add plus noise in the momentum, I get this magenta curve, so you get some kind of random shape, right, around it. Now if I use the new methods, I get this blue curve where the trajectories are quite noisy, because I have noise in the position equation, so every time step I perturb the position, not just the momentum. And I can get similar looking shapes, right? Now the trick is, if I want to increase number of landmarks, So I double them. Then in the random forcing case, because each landmarks have their own noise, then this will be a very wiggly line because they all don't talk to each other really, right? In this case, in the case we are doing, if you have, so sorry, I didn't say, those dark dots are just the centers of the noise fields. So think about blobs of noise like ellipses here around. So if the particle goes near this one, it feels this noise. If it goes near this one, it feels this other noise, right? If two particles are nearby this one, they shake together the same. So then obviously we get the same kind of blue line, which is a bit random but not too much, right? So we can control, what it means, we can control the spatial correlation of the noise. We can say we don't want to have very noisy image at the end, we just want to have some variability of the image with some, whereas in the normal one you can just, you can't control this, right? So then if you increase the number of noise fields by twice, you can get the wiggly line if you want, and so on. So you can have more control on this. Now the last point quickly is to try to, given the variability of the image you get from the data set, so given the variance around the mean trajectory here, how can you get back where to put those black dots and how much noise you need to put where to actually model the variability? So that's what we do here. So for example, in this case we had 5 landmarks as an ellipse moving also in this other ellipse, and we just put black arrows as the parameter for the noise. We just simulate Monte Carlo many solutions, which are the black curves here for the variance of the uncertainty of the noise. And then we try to infer what are the parameters for those crosses to get back the same. And then using so it's very difficult inverse problem, but if you use genetic algorithms, you can actually find in a simple case quite accurate model for the noise. And the last one is we just tried with this corpus callosum. So it's part of the brain. You can have many images. I think it's from 50 images. You can compute some of the gray shade is just the variance of the curves around the mean. And then we want to try to put, so the red crosses are just the noise field found from trying to reproduce the black circles using the blue circles. So how much noise you need to actually model the variability of these 50 shapes, I think. And by just doing a rough solution, you can get quite accurate some places, and you need to actually maybe move this noise here a bit, and then it's a difficult optimization problem, but I think can be done roughly. So okay, I'm done. So this is just a paper on the noise with street that Dalholm wrote. This is the big one, just accepted in the journal, and then this is a conference one with more examples. So if you want to read more, you can. And yeah, okay. Thank you.
Thank you very much. Thanks a lot, Alexis. I suggest that we postpone all questions to the lunch break.
The thing is, I have to go because I have my graduation day at 4.
Okay, so email Alexis.
If you want to I have to escape at some point. And,
okay, so have a good graduation. Okay.